So scientists have been working to achieve the practical nuclear fusion reactor for more than 70 years because fission reactors are practically possible on Earth as the heavy nucleus break down into a lighter nuclei by the help of neutron. But fusion reactors are like a small scale is there, but on a large scale practical use is still we are not able to achieve that. So far, this has been with only limited success. Explain the difficulties involved with the fusion as a viable source of power on Earth, and you should include reference to the condition necessary for a fusion to occur. Why are nuclear fusion reactors still we are not able to produce them practically or a large scale as compared to even though fission fusion produce greater energy than fission. Like if one mole of a fusion happened with the particles and 1 mole of a fission, fusion produce more energy. But why practically still like we are not able to do this? So what are the difficulties related to this? Number one, and what are the conditions? First thing, we need a very high temperatures needed. To overcome, because when two nucleus we want to fuse them together, the nucleus have the like charges and like charges repel each other. So very high temperature to overcome the electrostatic repulsion between the nuclei. That is one thing, that is a one difficulty. So we need very high temperature to carry out this. These conditions are there existing on like different star. That's why. Second thing, we need a high density. Why very high density? To increase effective collisions. For sustain or to sustain a fusion reaction. And another practical problem when if a material undergo a fusion reaction or a fusion, what happen on Earth if it come in contact with a container or a surrounding, it will lose its energy. So if a material undergo a fusion reaction, as a result, what will happen? Um, Contact with a container, the temperature will drop, or the container of a material or the container might melt when it come in contact with the container. And we to confine the plasma like the nucleus, the confinement problem is there. We need very strong magnetic field to confine the plasma, like to hold the plasma, to keep the plasma in the specific region. Or the nuclei, you can also say. So these are the problems which, so for a nuclear fusion reaction to occur, we need a very high temperature. We need a very high, why we need a high temperature to overcome the electrostatic repulsion. We need very high density so that they will have more effective collision and we have a sustained fusion. And if the material undergo a fusion reaction, it might, like if material undergo fusion reaction, contact with a container, it might drop the temperature or the container would melt because of very high temperature or energy. And the second thing, the confinement issues are there. Like we have to trap within the container, we have to trap these nuclei. For that to trap these nuclei or the plasma, we need a very high, a strong magnetic field. If the magnetic field is weak, then we won't be able to confine this. Then question 22. We have a Ganson can be produced by firing a calcium ion at a target. Californium CF atoms are there. The number of the neutron are produced in a nuclear reaction. Complete the equation. So because the total nucleon number should be same, this is 48 and 249. So the nucleon number, when we sum this, so 48 plus 249, 297. So this one is 297. So this should be 297 as well. Neutron is 1 and 0. So how many, this should be, this will be multiplied by 3. This down bottom is 280. See how ions of this energy could be produced. Like calcium ions were accelerated to an energy of 245 mega electron volt. How we can basically, we need a particle accelerator by using the particle accelerators. We can use them. It claimed that the calcium ions with an energy of 245 mega electron volt are traveling relativistic speed. Relativistic speed means like moving at a speed of light. Assess the validity of this claim. The mass of a calcium ion is given to you. So from the energy, we need the speed. So kinetic energy, EK, is equals to half mv square. But this energy is mega electron volt, but the formula is always in joule. So first we have to convert the mega electron volt into joule. So 245 mega electron volt, it will be 245 into 10 to the power 6 electron volt. And then we can, 1 electron volt is 1.6 exponent minus 19. So we convert into joule by multiplying with 1.6 exponent. So the total energy will be 245 into 10 to the power 6. That is in electron volt. Then we multiply by 1.6 into 10 to the power minus 19. That is joule. Plus half. The mass is given, mass of a calcium ion is given in atomic mass unit. One atomic mass unit is 1.6 into 10 to the power minus 27 kg. So to convert this into kilogram, we have to multiply by, so this will be 47.95 times 1.6 into 10 to the power minus 27. This will give us in kg. So the mass should be in kilogram. The energy should be in joule. And we have V square. So we just solve this. So this will be 2.45 into 10 to the power 6 times 1.6 into 10 to the power minus 19 times 2 divided by 47.95 times 1.6 into 10 to the power minus 27. And because this is V square, but we need V, so we take a root both sides. When we take a square root both sides, this will give us the value of the speed. Which is about 3.14 into 10 to the power 7 meter per second. So 3.14 exponent 7, and what is the speed of the light? The speed of a light is 3 into 10 to the power 8 meter per second. So It is closer to speed of a light. Not exactly, but it is closer to speed of a light. So using the kinetic energy and the mass, we can work out the speed at which the particle will move. The isotopes are there. 294 is extremely unstable and decay by alpha. After 2.5 millisecond, a sample contains 500 atoms. Calculate the original number of atoms. So the half-life is given milliseconds. So we have the formula n is equals to n naught e raised to power minus lambda t. And what about the lambda? The lambda is a decay constant which is 0.693 over half-life. That is a formula for the lambda. So 0.693. If the units are same, like this is millisecond, so the unit conversion is not that important. I can simply, without converting that, you can convert into second as well, it's fine. So the half-life, that is given 0.89 into 10 to the power milliseconds, so minus 3. When I simplify, this will be 779 second inverse. So n is equals to n naught e to the power minus lambda t, where n is the number of the nuclei present. N naught is the original we want. So as they mentioned here in the question, calculate the original. After this much time, we have 500 atoms. So this is 500. N naught we don't know. E lambda, that was 779, and t, the time we are finding after 2.5 millisecond. So 2.5 into 10 to the power minus 3. This 500 divided by e raised to power minus 779 into 2.5 into 10 to the power minus 3. This will give us n naught. Like how many original nuclei were there? So when we work out n naught, it will be 3,500. So 3,500 atoms were there. In the beginning, after this duration, 2.5 millisecond, we will left with 500 radioactive nuclei.